Hello and welcome. I am pleased to announce our next virtual broadcast titled Upwind Protective Action Decisions. It is presented by Chuck Reeves, and Chuck has been the lead analyst for the Pantex Emergency Management Department and Consequence Assessment Team leader for nearly 20 years. He's an avid EMI SIG member and he loves the outdoors and nature. So great. Me too, Chuck. Hopefully, we can all get outside later this afternoon or this evening. If you have a question during this session, please use the chat tool on the right. Type in your question there, and I'll relay that to Chuck at the question and answer session at the end. And with that, please welcome me in welcoming Chuck Reeves to our virtual stage.
All right, I'm going to speak today a little bit on upwind protective actions for larger hazardous material release. As an aside, something before that, I have some photos from our new optical lightning detection system at Pantex. Because we work with explosives at Pantex, being careful around lightning is very important to us, and the optical lightning detection system is a system that uses cameras to watch lightning and can determine exactly where lightning would strike on the plant. The cool thing about it is it's essentially a robot that is taking pictures of lightning every time there's a storm, and it takes some absolutely fantastic photos of lightning strikes. So I'm going to just run through a few shots of those. They are really gorgeous shots, gorgeous photos. So there's one. There we go. Some cloud-to-cloud lightning. Cool, big ground strikes. Some of these look like they're scenes from Harry Potter films, I think. See all the lights from our security systems down in the background with being lit up by the lightning overhead. Get some gorgeous shots of the sky here on the prairie. Amarillo is a home to really beautiful sunrises and sunsets, and the lightning strikes just kind of set that off, I think. We get some really fantastic fireworks shows out here when we're in the spring thunderstorm season. The tree of light. So those are my lightning shots. Our system, because it runs literally 24/7 and is looking at the sky for lightning shots, we actually have thousands of photos of lightning. But that's not my presentation. Here's my presentation. We're looking at upwind protective action decisions for hazardous material emergencies. And the problem is we could have a emergency with a very large isolation or protective action zone. And if we combine that with 360-degree protective actions, we could make response difficult, make it difficult for our responders to move in, stage, and deploy to mitigate the emergency. Also, it could make it harder for our sheltering personnel if we need to move them, evacuate them, whatever else we need to do. It just becomes a little bit more difficult if we're having to maintain a large 360-degree perimeter of protective actions. So we've got our isolation zone and protective action zone. My next diagram will show those a little bit better. But one of the important things is the initial isolation zone and initial protective action zone. The difference between initial and non-initial is really one of the key points to what we're moving into here. We are going to try to get past initial, and the initial is those pre-planned things. In case of a hazardous material emergency, this picture came right from the DOT Emergency Response Guidebook, and it's one that's widely distributed. So you have the hazardous material release at the black dot in the middle, and then you see the circle around that where you develop your initial isolation zone for hazardous material releases. That's usually developed out to your threshold for lethality distance, and then the downwind distance goes out to your protective action criteria distance, usually determined from some very conservative criteria. This is the keyhole response plan. shown like this. A frequently asked question posted to NA41 asked a question about keyhole concept and initial protective actions. And the response says a lot more, but I sort of boil it down to the keyhole concept is not acceptable for immediate initial protective actions, but would be acceptable for follow-on actions once baselines have been established. The keyword again on this is immediate and initial. The conclusion is we need a tool. We need this decision tool to help us go from that immediate and initial time frame where we're just operating on the pre-planned, very conservative 360-degree perimeter to something that is more sensible and allow a smooth follow-on emergency response. We need to do this for our incidents with larger, our operational emergencies with larger initial isolation zones and protective action zones, and develop protective action decision-making tools to assist in transitioning from those initial zones to a more narrow follow-on isolation zone and protective action zones. We don't have to do this for small emergencies or smaller, shorter-reaching initial isolation zones and protective action zones, because there's not a lot of benefit to narrowing it down. In those, we can remove bystanders around relatively easily anyway, and we can get our responders into a reasonable spot where they can effectively mitigate the emergency on their own. So we're concerned about wind shifts. So I've drawn the same thing here, but I've drawn it with a 360-degree circle, and then you see on the far left with the 0-degree wind shift, it's not going to move at all. We're doing 360 degrees initially, largely to be cautious against a wind shift that might create a hazard someplace that wasn't just downwind of the original emergency. So what was it, 30, 60, 90 degrees? What's the significant wind shift? For my study, I picked 60 degrees, so it would be the second from the right image here. If we have a wind shift that wide, then I'm going to say it is dangerous outside of just being downwind. If it's within that cone of 60 degrees left or right and the original direction, then I'm going to say that's okay. We can work with the upwind side of it and reduce that protective action zone and isolation zone and work with the upwind side of it. The first analysis was done by Tom Bellinger at Y-12. Really good work. He looked at wind speeds and wind changes and wind directions at both Pantex and Y-12, and noticed that above about 8 miles an hour, we can see at both Pantex and Y-12, the winds tended to stay within a 30-degree cone of the original downwind distance. Helps us more at Pantex because we've got higher wind speeds. Y-12, they have slower wind speeds because they're in the mountains and we're out on the prairie. They have more wind shifts to cope with. That was a great first cut. At above 8 miles an hour, the winds rarely shift very far. At windy Pantex, we have 8-mile winds more than 70% of the time. So that helps us a lot. I wanted to see if we could get a little bit more. So I looked at the Aloha consequence assessment model that NOAA produces, and they have a feature called the confidence line, or sometimes they call them the ladybug lines because they'll form lines that look like the wings of ladybugs. Those are those black dotted lines you see in this image, and it represents what NOAA has decided is within a 1-hour time frame, the plume is likely to remain within that confidence line 95% of the time. So they statistically went out 2 sigma for that. A couple of examples. This is the exact same release run through Aloha. I ran one at 4.4 meters per second in D-stability, and you see that long cigar-shaped plume, and the kind of narrow, long set of confidence lines. They run the exact same scenario, just change the wind speed and stability class, and down to 2.5 meters per second in A stability, and you see it not only the plume shrink and get in length, but get a little wider, but now you see those confidence lines going out to that big bell shape. That's meaning that we're a lot less confident that the plume is going to keep going that same direction downwind, and it may swing more widely. Aloha, I spoke with the developers at Aloha, and it took a couple of few email exchanges with them. The diagram you see up at the top in the first calculation, that's what's published in the Aloha manual, and it didn't quite describe what they were doing. So I ended up having to follow on with the Aloha developers, and the part of the formula that you see in red in the second line is what they provided me, and that's actually something that's happening behind the scenes in Aloha that's not in their manual. And it shows a modifier as the wind speeds are below 4 meters per second, down to 1 meter per second, that the confidence lines become wider and wider until they become a full circle. Below 1 meter per second, they show the winds, the confidence line as a full circle every time. So I ran that. I took that and took a sampling of Pantex data and plugged the formulae in, and that's what I saw. For each of the different confidence lines, you can see, for each of the different stability classes, you can see how the confidence lines are drawn here in degrees. Where if it goes out to 180 degrees, it's wrapped around to a full circle, and because it got into 180 in both directions. Or different 10-meter wind speeds here. You actually, to do it running the Aloha calculation, you have to power law that down to a 3-meter wind speed, oddly, but that wasn't hard to do for Excel. So you see what the lines look like here at different wind speeds. You see F stability swings widely a lot, and you see like that solid blue line for D stability, that's like the least likely to swing on you. So if I use Pantex data and I ran these confidence lines, the Aloha confidence lines bounded any wind shift within 1 hour for 87% of my sample. This is probably very significantly different from what NOAA found in their sample cases, where they bounded the wind shifts for 95% of their cases. This may just be a difference in one data sample versus another. Additional data analysis, I ran this for every 15 minutes of weather data at Pantex from October 1, 2016 through midnight of November 1st, 2019, 108,000 measurements. And so that's what 108,000 dots looks like in a Aloha plot for wind speed and wind shift. And you can see the wind speeds plotting on the right-hand, on the left-right x-axis, and the wind shift in degrees on the y-axis there. So you can see they shift a lot at low speeds, and they don't shift very much as the wind speeds go up. You know you're at Pantex when you have 24 meter per second wind speeds for a 15-minute average. So I took the Aloha plots for each of those points and ran it on top of the Pantex data. So there's that 87% set of lines where Aloha is accurately predicting the bounds of the wind shifts for 87% of those dots. So if I look at that 60-degree wind shift and block out where is a 60-degree wind shift becoming significant, then you see relative to 108,000 dots, you see a relatively few dots up in that yellow box that I show on top. We're getting to statistical insignificance here, I hope. Of the dots in the yellow box, those 189 cases out there show that we are now getting to 99.83% accuracy. And we've helped in that 2.5 to 8 mile an hour wind speed range a lot. If we take out wind stability classes, A E, and F, Alpha, Echo, and Foxtrot, then we actually take out most of the big wind shifts. Stability classes Bravo, Charlie, and Delta don't shift nearly as much, even at lower speeds. But below 2.5 miles an hour is always a big wind shift risk. It showed up all across the board on my data. So here's what we're looking at for a decision tool. We're looking at, do we have a large initial isolation zone and protective action zones? If not, we don't need to bother with this. If yes, is the wind speed less than 2.5 miles an hour? Again, we've got to continue with 360 degrees because below 2.5 miles an hour is really scary. If it's greater than 8 miles an hour, we can reduce our IZ and TAZ right away. 2.5 to 8 miles an hour, then we got to look at stability class. Our weather tower gives us that through as a measurement, as a calculated measurement, and so we can build a decision tool to go from that initial pre-planned 360-degree protective action zone down to something that's where we can use the upwind side of it better. This is still a bit of a work in progress. We have got this far. We have not done full implementation with this at Pantex. I've started to run this same calculation with Y-12's data. That is not complete yet, so that's still a work in progress, and we have not implemented this for our responders in the field yet. There's some other hazards that we need to pay attention to aside from just wind shift, and some of these don't affect Pantex. For example, terrain steering, because we are a wide, flat, open piece of prairie. But if you have a jet release, if you've got dense gas slumping, or you've got a running evaporating pool, then something more than my wind shift may complicate the scenario more, and using just my methodology probably isn't appropriate at that point. Another one to look at, just to kind of bounce this off of, is the Utah Valley University study for the Department of Homeland Security called Project Jackrabbit, where they released very large quantities of anhydrous ammonia and chlorine in simulated urban environments. They actually released very big quantities of hazardous material out there in the desert, and they measured their upwind hazards under different conditions. That's one of the kind of the bounding points I'm looking back at every time I produce something with my analysis and saying, okay, am I jiving with them? And so far I am. Anyway, as we move forward, again, if anyone has some weather data and would like to get a copy of my spreadsheets and actually punch your own data into my spreadsheets and see how your site's weather data looks on my plots, I'm more than happy to share the spreadsheets with you. And if you've got ideas on ways that we could use this and further implement it, I'm more than happy to hear those. Given that, that is the presentation I've got for today, and I want to thank you all for your time.
Wow. Thank you, Chuck, for your wonderful presentation. So much good information. And those lightning shots at the beginning, they are just awe-inspiring, and I'm sure everyone felt like I did, and they're just breathtaking. I have been monitoring the chat and the questions that have come in, and we do have a question for you, Chuck. It says, in what time frame do you imagine applying the decision tool that you showed?
So I would imagine perhaps sometime at dispatch, perhaps once the initial call comes in, we could have a display that the fire officers or other emergency responders could look at rapidly before they do their route planning to respond to the scene, or perhaps our at the dispatch center or in our operations center, someone might have a chance to look at weather data at that point and make some decisions. If not, it could be delayed, and they could respond, and then the consequence assessment team could do a follow-on check on that.
Wow. Good. And another question that has come in is how do you imagine responding in times when wind speeds are below that 2.5 mile per hour range that you showed, and your data showed that that's the biggest wind shift?
Right. The emergency responders are still going to have to move to mitigate the emergency. They're just going to have to be in proper personal protective equipment to do so. That may be very awkward with a very large release, but we've at least reduced the number of times that they might have to respond in that awkward way using this decision tool. The bigger advantage of it, of using the tool, is going to be in perhaps freeing up people to take further protective actions, such as transition from sheltering to evacuation. At those very low speeds, we may just have to continue to keep people sheltered.
Wow. So important, such important information. And finally, how do your responders get the wind speed and the stability class information?
Right now, they're not receiving the stability class during their initial response. During initial response, um, the dispatchers, the fire dispatchers here, when they call out a call, they provide that because they're seeing a display of the weather tower in the dispatch center, and they're just relaying that out as they send the responders out.
Okay, great. Boy, we sure appreciate all this great information, Chuck. And we have reached the end of this session, but if you have other questions, you can send Chuck an email. His contact information can be found in the speakers tab. Be sure to give Chuck some feedback by going to the survey icon at the bottom of your Attentify app. And you can give Chuck some feedback there and also receive credit for attending this session. Our next session is going to be bringing it all together, facility preparedness program with a great team from Lannel, David Silver, Joshua Miller, and Anna Strong. You can select that session on the left when it begins or join another session, and we look forward to seeing you back soon. Thanks.